Welcome to this video. In this video, I will be talking about the bit flip code and how it corrects errors of bit flip error in qubits. So the idea is it's a 311 code. So it encodes. So inside the encoder, I get 3 physical qubits, and there is one logical qubit that I am encoding into, and it cannot detect single errors even. So if I have a bit flip circuit, it will not detect phase flip error. So it is not that useful, but it helps in showing the criteria and how particularly stabilizer formalism works. So here again we will see the code space, the error space, and the stabilizers, how they commute and anti-commute to finally give the proper syndrome. So this part before one, this part is called encoder. This is where I get my errors. So this will be bit flip errors, and this entire part that is our main lookout is called syndrome extraction. Syndrome extraction. So let's start. So basically, we have a state psi which is alpha 0 plus beta 1, and then we send it through the encoder and we get a state alpha 0 logical plus beta 1 logical, where L stands for 0 0 0 and 1 1 1. So this is kind of the majority voting and like the repetition code. And then the C here, the code space is span of this thing. So this was also kind of similar in the previous case where we saw the 211 code. And now we have a different kind of errors. So we can have error in the first qubit, we can have error in the second qubit, and we can have error in the third qubit. So we have three different error spaces, f1, f2, f3, and the stabilizer for this is written as this. I will explain this notation later, but what it means is that it's good to think of it as a set for now. So it is the set of z1, z2, z2, z3, and the product of them. So these are called something like the generators of a group. So the product of them will be z1, z3, because z2 square will be identity. So this is the S. This is the kind of curly S. And what happens is now we will proceed to analyze the circuit of this bit flip operator. So what happens is we introduce error E after the step 1, and at the step 2 what we are doing is we are taking two ancilla qubits. So these ancilla qubits are 2 in size, and they correspond to the size of the stabilizer generators. So I have 2 generators here, so that's the size, because I have to detect these both generators. And then I apply Hadamard gate, and based on this, then the next point is to apply the conditioned these operators. So conditional z1, z2, and z2, z3 operators, and which I have applied in this particular line here. And now what I do is I apply the Hadamard gate again. So there is one Hadamard gate after and one here. And what they do is they again split 0 1 0 0 into linear combinations of 0 and 1. And so I can collect these combinations, and what I get is something that I have shown here. So you can see that this is very nicely structured. The positive signs and negative signs, we will soon see that they come in a very particular fashion based on the anti-commutation relation with the errors. So now what happens is that the syndrome is what we measure out of the ancillary qubits. So these 4 are the syndromes. So as you can see, if nothing happens, then what I get is identity or bit flip on all the 3 qubits. But for example, now the error channel is such that there is bit flip on like 1 qubit. So we will not talk about bit flips in 2 qubits or 3 qubits. And in this case, what we have is 0 0 corresponds to nothing occurring. 0 1 corresponds to a bit flip in the third qubit. We are getting information about the position of the qubit also. And bit flip on 1 qubit corresponds to a syndrome of 1 0, and bit flip on 1 1 corresponds to a syndrome of error x2. So why this is the case, let's quickly see. So the case is particularly if we talk about x3 commutes with z1 z2. Why you can easily verify this. X3 commutes with z1 z2, but it anti-commutes with z2 z3 and z1 z3. So because of this I have two minus signs which becomes plus, and this probability becomes 1, the probability of obtaining this state, and all other probabilities goes to 0. So that's why when 0 1 clicks, I know that x3 must have been the error, and then I can apply x3 again on the third qubit to flip the error, and I have corrected my error. So this will only work when I have single flips. And similarly you can check that x1 detects 1 0 because it anti-commutes with z1 z2 and z1 z3. It is in fact easy to see because x1 has a different operator z1 here, and this also has z1 in the first, so they will anti-commute. So similarly for x2 you can check by your own, and this means I can detect it and I can correct the flips. Now how can I detect phase flips? So for this what we can do is we can use a simple trick, which is that a phase flip is like a bit flip but in the plus minus basis, because application of z to plus state gives us a flip to the minus state, and z to the minus state is a plus state. So what we do is we modify or rotate our code space to this particular space here. So this is our code space, and this code space is obtained by encoding circuit encoder of this form. This is the encoder, and so this is the state, and the idea is now how we will detect the errors. We will perform this syndrome extraction circuit by using x1 x2 and x2 x3. So you can check that these are stabilizers because x1 x2 keeps this space invariant, and x2 x3 also keep the same space invariant. So in the previous circuit I will just make two changes. I will make the change in the encoder and make the change in the syndrome extraction. So with this, let's properly define what is a stabilizer group and what is a stabilizer codes. So the main definition starts from n-qubit Pauli group. So a Pauli group is a group. So a group has four properties. It has the property of closure, property of associativity. So closure, associativity, existence of identity, and existence of inverse. So these are the group property, and Pauli group will also have this property, and it is defined like this. Over an n qubit we choose this omegas to be powers of minus 1 minus powers of iota 1, minus 1, iota, and minus I, and then we have p1 to take value between I, x, y, z. So basically the Pauli operators. So these all these operators, if you collect, they form a group, and that is called the Pauli group. So there are 4 power n plus 1 elements in the group. And the second definition is what is stabilizer group. So before that, let's look at the properties. So square of any element of the Pauli group is plus 1 or minus 1. The elements of the Pauli group either commute with each other or anti-commute with each other, one of the two. So these properties are simple to verify, and based on this we define the stabilizer group as an abelian subgroup of the Pauli group, such that an important condition is that minus identity which belongs in the Pauli group does not belong to the stabilizer group. So let's break this down. So this is the important definition, one of the most important definition. So it's an abelian subgroup. It means that the elements commute. So the elements inside the Pauli group will commute with each other. So the group property, the group operation that I am talking about is nothing but multiplication of two linear operators, and this means they commute. And minus identity does not belong to the stabilizer group. Why this property is crucial, we will see in just a second, because it will be crucial to define what is a stabilizer code. A stabilizer code is nothing but collection of the states psi such that they lie in the +1 eigenspace of the stabilizer group. So they are invariant under the stabilizer group. So now if you see that minus identity is not included, because minus identity will have all the eigenvalues as -1, and that will make this entire code space trivial. So this is a non-trivial code space because minus I is not in the stabilizer group. And this means that at least one eigenvalue will be +1. So because p square is +1 or -1, and this translates to the fact that one of the eigenvalue is +1. So with this I will just talk about bit flip code and phase flip code. So the bit flip code was written as this: Z1, Z2, Z2, Z3, and this symbol is for the generator. So I can write my stabilizer group as G1, G2, G3 ... Gm, and this, it means that I take the independent group elements such that all the group elements can be generated by multiplying these elements together. So by multiplying I can generate new elements, and that's what this means, this symbol that I put on both sides. And the main idea is that just by defining this, so just by saying that my stabilizer is this or my stabilizer is this, I am defining a code space that is the stabilizer code. And this is the main idea. So instead of thinking in the state picture, instead of always giving my code space, my error space, I think in the operator picture that what is my stabilizer. If you give me a stabilizer group, I have a code space automatically. You give two different stabilizer group, I will have two different code space. So with this I end this video. In the next video I will be talking about the Shor code, which will be an example of code concatenation. I will also talk about 422 code, as you can see, which is the smallest code that detects both the bit flip and phase flip errors, but it does not correct the error, it only detects them. And that's it. So let's go to the next video.